Hello and welcome back. Let's continue with our lecture on general theory of relativity. In the last lecture, we have seen the derivation of Lorentz transformation, which essentially says that the velocity of light is same for all inertial observers. Now we go ahead and use the concept of time, spatial distance, and the four velocities and particle motion in the Minkowski space. Now here we are going into general relativistic mechanics, which means that our space-time is four-dimensional system. A simple particle will have a 4 degrees of freedom, that is time, and 3 spatial dimensions. So let's continue. We talk about particle motion in Minkowski space-time. This is part of course PH4205 at IISER Calcutta, and I am Rajesh Kumble Nayak. Let's see one of the important properties of Lorentz transformation. In the last lecture, we have seen Lorentz transformation is mainly coming because of preservation of velocity of light, or what we call is if the event is null separated, then it is null separated in all inertial frames. So this is one of the condition we have used, and we have obtained important property that the Lorentz transformation satisfies that lambda mu nu, lambda mu sigma is equal to delta nu sigma, or in terms of matrices, lambda transpose into lambda is equal to 1, which is a property of orthogonal matrices. Let us quickly recollect some of the important property of orthogonal matrices. We know that orthogonal transformation preserves magnitude of a vector or distance between the 2 points. It also preserves the dot product between the two vectors. Since the Lorentz transformation also satisfies similar property, it can be easily seen that the Lorentz transformation also follows a very similar condition. It's not just null vector, it is a dot product between any two vector remains invariant under Lorentz transformation. To pictorially see it, for example, let's say that we have vectors which are null, time-like and space-like. After a Lorentz transformation, they will preserve their property. So that means null vector remain null and the time-like vector remain time-like, and so does space-like vector. That's a very important property which we will be using very often. Before going into any further, let's quickly look at the idea of time. Because idea of time is very difficult to explain. Time or kal is referred to as a death in India, or it also referred to as a truth. Instead of going after defining a time, let's simply define a practical way of doing it. That is, how do we measure the time? That basically is the clock. The clock essentially measures an event which is happening in the specific interval, and that interval, the smallest of it, is what we are interested in, and that is called the ticks. This ticks is the smallest unit which you can measure. Now it depends on the technology or amount of money which you have to build a clock would decide the tick. For example, if you use heartbeat as your ticks, then you have approximately 72 ticks per second. On the other hand, if you have a digital clock, the ticks would be of the order of 1 million per second. You can have a more and more accurate clock by having larger and larger ticks per second. So if you have cesium clock, to date probably is one of the most precise clocks. You can have 10 to the power 13, 14 ticks per second. So this refers to how much precisely you can measure. Once you have your ticks defined of your clock, you can compare it with the other clocks, and you can transform your clock reading to another clock reading. As per Newton, it is a global time, which means that one can simply convert these ticks, scale them, and you have your time transformed. In the case of special relativity, however, these ticks don't simply transform into time from one observer to another observer. The velocity or speed at which each observer is moving will appear into these ticks. That is what is a Lorentz transformation, which decides how the clock should behave or how time transforms from one observer to another observer. That is basically is the story of time transformation. leave the detail or to your imagination. Let's work on what is practically needed. The first and the simplest of time which we have is a coordinate time. The coordinate time, as we see that four-dimensional space-time event are referred with the four coordinates or 4 degrees of freedom. The zeroth component is the time coordinate. This is called the coordinate time. Like generalized coordinate system in the Lagrangian mechanics, a coordinate itself do not have any meaning. That is what mean to is the time interval or ticks could be anything. It could be Galileo's heartbeat, or it could be swing of a pendulum, or it could be a tick of cesium clock. What is important is the proper time. Let's say A is designated with the coordinate system x mu and B is given a coordinate of x mu plus dx mu. The space-time interval between these two events A and B is what we call the proper time between the event A and B. So it is defined as ds square is equal to g mu nu dx nu, where g mu nu is the metric. Now in the space-time diagram, you can always mark them as you have an event A which is happening at x mu, and you have an event B which is happening at x mu plus dx mu, and then you have interval in them. Proper time is given as a space-time interval between event A and B. You can always project them on your coordinate system. The coordinate time is a dt, and you also can have coordinate spatial separation dx. But what is more important is a proper time which is invariant under the Lorentz transformation. Now in the case of Minkowski space-time, you can replace the metric by Minkowski metric, that is ds square is equal to eta mu nu dx nu. So that defines the proper time between the two events A and B. Now you could have an event B at the same spatial coordinate as event A, then the space-time interval simply becomes the coordinate time interval, that is ds square become dt square. That is true only in the Minkowski space. Otherwise, proper time and coordinate time would be always multiplied by metric component g00. For an observer who is fixed to an inertial frame, then the coordinate time and the proper time are going to be same. Relation between proper time and coordinate time, we have two events A and B, and the space-time interval or the proper time is given by ds square. This proper time make only sense for the event which are separated by time lag. In the case of events are separated by null, the space-time interval ds square becomes 0 and the proper time do not have any meaning. Let's take a proper time for a time like observer. We have already seen that is given as a ds square is equal to eta mu nu dx nu. Explicitly one can write ds square is equal to dt square minus dx square minus dy square minus dz square, that is equal to 1 minus dx square by dt square. Where was missing here? Basically you can pull out dt square and write dx by dt as velocity. We know that that is equal to 1 minus v square, and we can simply write it as a 1 minus v square into dt square. Now we know that this term is connected with gamma. Let us pictorially have a look at it. We have a space-time diagram. You have a space along x-axis and time along y-axis. A rest observer who would be following constantly with time and whose coordinate time and proper time do not change. On the other hand, if observer is moving with the spatial velocity v, whose world line, that the path which is traveled in the space-time diagram is called the world line, will be still straight line but will have an angle theta with respect to the time axis. When theta is 0, then you have observer rest with respect to the frame, or the velocity v is 0, and then theta can go maximum up to 45 degrees, and that is when velocity becomes the velocity of light. Because theta can only approach 45 degrees, it cannot in principle for a time like particle to achieve the speed of light. That is reflected in terms of a proper time which is taken in the interval. The proper time becomes 0 when it moves at the speed of light. So this way one can relate the proper time to the coordinate time with this relation ds square is equal to 1 minus v square into dt square, or dt square is connected with the ds square with this relation. Both relation shows how the time can be transform from one to another. Because we see that time dilation essentially is the interpretation of this result that the time for a moving observer would always look lesser. So this is a way of interpretation. We need a more understanding of time that essentially would come when we do general theory of relativity. All which says here is that amount of coordinate time would blow up as v tends to c, or no time-like particle can approach the speed of light. Only light can travel with the velocity c. Now, another closely connected concept is a measurement of spatial distance. I am here doing a little bit more general derivation. However, we require a limited version. Later, you would see that it is good to have this concept understood very clearly, that we need to involve light for measuring anything. We have a one universal concept, that is the velocity of light, and then we have a concept of clock. Once we have that, these two acts like our fundamental measuring tool. Distance between any 2 points would also requires the involvement of time. Now, if you look at the space-time diagram, we can have a two observer A and B who are time-like, and then we want to measure the distance between them because time is relative. Now, one problem comes: if both observers are rest, then there is no problem. One cannot use the coordinate time to measure distance between the point. However, if the observers are moving, then you would have certain difficulties because each of them would have their own clock which would be going at different ticks. One need to transform them, compare them, all kind of difficulty might be coming up. So one of the interesting way of measuring the distance between the 2 points is basically by forgetting the active role of B itself, except telling that the B carries a mirror and the A carries a light source, and all the measurements are done with respect to A, his clock, and his coordinate system. Now, observer A will send a laser beam simultaneously starting the clock, and then that would go to the observer B and reflect back to observer A again. The A will note the time when he leaves the laser beam and get back it and calls the time interval as a 2dt. Then the spatial separation between A and B is simply given by C into dt, would give you the spatial distance between the 2 points. This is a self-consistent way of measuring all the distance. You do not have to involve B in any way. Their clock or their motion will be already registered here, as the light will have to go there and come back, and all the information is decoded from time taken by the light to go and come back. So we can mathematically do this too. The light is propagating from A to B, so that should satisfy the condition d square is equal to g mu nu dx nu is equal to 0. Now we can explicitly write down in terms of a time and spatial coordinate, that is 0 is equal to g00 dt square plus 2g0i. I goes from 1 to 3, so dxi's are only spatial displacement, and dt into gij dxi dxj. Now we need to find out dt, that is the time taken by the light. So we can solve this quadratic equation very easily. It is well-known method. We get is that dt is equal to 1 by 2 g00 into minus 2 g0i dxi plus or minus square root of 4 g0i g0j dxi dxj. Note that how I have taken the square. I simply did not square. You would have written that g0i dxi into square. So this would be very confusing notation because squaring would be fine, but the tensorial way of writing is that gxi into g0j dxj. So this way you are doing the product without mixing up the indices. And then we have a last term which is 4 into g00 gij dxi dxj. This can be easily simplified with this very complex notation. You might be again asking, why do all this trouble? You should know that this gives a very interesting result. It looks like that when g0i, the cross term in metric, is not 0, then light is going to take different time to go up and come down. This is an interesting scenario. Unfortunately, that does not happen in the case of Minkowski spacetime. In the Minkowski spacetime, there are no cross terms, and we usually refer this plus plus or minus, plus for the forward direction and negative for the reverse direction. That is, this is a plus direction of propagation of light and this is a minus direction of propagation of light. From that way, this is a forward and this is a backward direction to the measurement of time. Now we can go ahead and compute this in the Minkowski space-time. All we have to do is substitute g mu nu by eta mu nu. Then we simply get dt is equal to plus or minus square root of dx square, and then you see that it is a plus or minus dx, one for the going up and one for coming down. Round trip time would be dx. Since we have taken the velocity of light to be 1, space and time are measured with the same unit, so that way the amount of time taken itself is a distance between the points. So this is a way of doing all the measurement. Without the light, we cannot in fact measure the distance between the points. Though it is complicated, the main idea here is very important. We will find it more interesting what happens in a rotating frame. In a rotating frame, time taken by light to go from A to B and B to A is not same. That we will do in a coming lectures. Let us go ahead this time and let's have a quick reminder about a curve. Curves which again and again came, we have blindly followed up without giving proper definition of what is a curve. Curve is basically a mapping from R, that is an interval A to B, so that we can call it as a time or some arbitrary variable, lambda, theta, anything you can call. It is basically an interval from A to B in R into your space. Space could be Rn, space could be curvilinear geometry which you are using, generalized coordinate of n dimension, anything you could have. So basically you have a real line in an interval A to B, and then you have your space M. Think it as an n-dimensional space, and then you have a starting point here. Curve need a starting point, and that would be mapped in n-dimensional space. And then it will have an end point, and then as a parameter changes from A to B, you will have point mapping into the space. So that is what have a particle moving given time interval A to B would be an example for the curve. Can also differentiate. We have seen that we can differentiate the curve and get the tangent vector, and that is also we call the velocity. In the case of space-time, the velocity is called 4 velocity, just to distinguish between the spatial velocity. Tangent vector with the parameter lambda here named is as a dx by d lambda. So it could be any dimension. In the 4 dimension we use Greek indices mu. It is an abstract indices. It is an n-dimensional space. You can have a covariant vector, contravariant vector. You can relate them through the metric. We are using only metric space, so we do not have to worry about other things. So once we have the understanding of what we call the curve, then we can have free particle motion. Let us look at the motion of particle. Let's say that we want to move from a point A with the coordinate x mu, that is 4-dimensional space-time t, x, y, z, to event B, that is given by the coordinate x mu plus dx mu. This seems to be missing here again. Plus dx mu. The coordinate explicitly given as t plus dt, x plus dx, y plus dy, z plus dz. In absence of any force, we know that in an inertial frame, it should be moving along straight line. Let us pictorially see that A is given by the coordinate x mu, B is given as a x mu plus dx mu, and then you have infinitesimal separation between them. The space-time interval or the proper time is given as a ds square is equal to dt square minus dx square minus dy square minus dz square. Trajectory as a curve, x mu of lambda, mu can be an arbitrary parameter representing the motion of the particle. So we have a free particle trajectory given by the straight line. Let space-time velocity is given by u mu is equal to dx mu by d lambda, that is also given as a x dot mu. So that is a notation which we are using. If the particle is moving along time-like curve, then we can normalize the velocity or 4 velocity as a u mu is equal to dt by d lambda square minus dx by d lambda square and so on is equal to 1. So this is basically a way of normalizing the tangent vector or velocity vector. So this basically means that we are using ds or proper time as our parameter to represent the motion. So this is one of the easiest way of parameterizing the trajectory with the proper time, or it is also called the arc length parameterization. In such case, velocity u mu get normalized, or we can see that directly in terms of here. If we use ds square as our parameter lambda, then your velocity would be always equal to 1, and such kind of parameterization is called the arc length parameterization. X mu be the trajectory of a time-like particle, and then we have the force velocity is given by ua is equal to dx mu by d lambda, that is equal to x dot mu. Now, if we are referring to a time-like trajectory, then we can always normalize, or we can always use the proper time as our parameter. Then we have u mu is equal to 1. If the trajectory is a null light-like, then we cannot normalize. And in such case, we have to use an affine parameter, that's basically an arbitrary parameter, such that the equation would be simply not. So we cannot use proper length parameter. Of course, in the case of space-like trajectory, we are not interested about them. We can use the length parameter there, but it doesn't have any physical meaning within the framework of relativity. When we formulated the special theory of relativity, we have kept the idea of inertial frame, and we have imposed the condition that nothing can move faster than light, or velocity of light is same for all the observer. Now we have the Newton laws of motion need to be applied, and that equation of motion basically can be written as a dp by ds is equal to 0 for the free particle where there is no force. It would be going along the straight line, and we can apply the Newton's law if we can construct the force momentum, which we can define from the force velocity, and its rate of change is 0, would give us the motion of free particle. In the presence of force, we will have to equate that to force. Generally, a better way of solving everything, we have seen that using the Lagrange equation of motion. Lagrange equation of motion can be easily transformed from one coordinate system to another coordinate system without even have to worrying about the inertial or non-inertial nature of the frame. So we can simply do the same thing with the special theory of relativity too. However, in this case, time also comes into equation of motion, and we can write four-dimensional kinetic energy simply taking the analogy from Newtonian mechanics, that is given as four-dimensional kinetic energy can be simply taken as a square of the velocity, that is a force velocity, and from that we get kinetic energy to be half t dot square minus x dot square minus y dot square minus z dot square. For the free particle, we know that the kinetic energy is a Lagrangian. So we have worked out all the details in the case of Newtonian mechanics. Now we can simply do the same algebra with four-dimensional notation. In the case of Minkowski metric, we can use this Lagrangian with 4 degrees of freedom t, x, y, z. However, we have one difference here. We have a time-like particle and we have a light-like particle propagating. In the case of time-like particle, we know that the kinetic energy, that is u mu is equal to 1. That is a kinetic energy, or Lagrangian itself takes the value of 1. That is one of the condition which we can use in the equation of motion, which is actually conserved here. And in the case of light, we know that u mu is equal to 0, and that also can be explicitly imposed. That is to say, Lagrangian takes the value of 0 and get the equation of motion for light. This is a way to get the equation of motion for time-like and light-like curve. So this way we can get the equation of motion, and we have already seen that for force-free particle we would get a equation x double dot is equal to 0. This should have been alpha. This is alpha and this is alpha beta gamma is equal to 0. We have seen earlier in the tutorial that if we apply that, we would get an equation similar to this. If the metric is constant, then gammas would be 0, and we would get this equation, that is x double dot alpha is equal to 0, and the particle would propagate along the straight line. On the other hand, if there is a non-inertial transformation, then this equation of motion, which we call is a geodesic equation of motion, had to be solved, and one can get the equation of motion from this. That is a way to get the equation of motion. Let's quickly summarize the notation and what we have said so far. So we are studying equation of motion. What we have is a velocity or force velocity, which is usually referred to as a u alpha upper 1 as a gamma into 1 plus v, where v is a spatial velocity. All Greek indices goes from 0 to 3 and Latin indices goes from 1 to 3. Now gamma can be treated as a normalizing constant such that the u alpha is equal to 1. We use proper time parameterization so that the velocity is normalized. U alpha with lower indices comes as gamma into 1 minus v. That is because of the Minkowskian signature, which is coming minus for the spatial one. The gamma is given as 1 is equal to gamma square into 1 minus v square. So it's basically normalizing constant. Gamma square is equal to 1 by 1 minus v square. In the case of light, usually for velocity, which is null, is written as u alpha is equal to 1k. K is a spatial direction along which light propagates. From the null condition, we have u alpha is equal to 0, which corresponds to 1 minus k square is equal to 0, or mod k square is equal to 1. So k is a unit vector. So in this notation, we can also write that as a u alpha as a x dot, y dot, z dot, and so on, and that is basically velocity defined with arc length parameterization or proper time. The derivative dots are here referred with respect to proper time, or s. We can pull out dt here, then we have a 1 dx by ds into ds by dt, and so on for the other dimension, which leads to dt by ds into 1 and dx by dt. So that gives you is the velocity. So in this comparison, what we have is a gamma as a dt by ds, that is at which the rate of change of coordinate time is given by that. So we have already seen the relation between the coordinate time and the proper time. So this is again comes up in the same way. This is where the spatial velocity is given as a v as a dx by dt, dy by dt, and dz by dt. That makes it comparison with the Newtonian equation very easy, because time is a Newtonian parameter and the velocity we can simply write as a dx by dt. We stop here and continue with the next lecture.